whatever it takes to get started. Everybody, thank you very much for coming for this very special event. We are looking forward to this interesting presentation by Bob Scholtz. Bob is finishing his 51st year in the department this semester, and but still there were few things about him I knew, but many things in his bio that I did not know. I did not know he was Lebanese because he's from Lebanon, Ohio. He's been. I did not know that he worked at. You worked for a long time, even after joining the faculty at USC. At Hughes Aircraft. I did not actually know this about him.
Don't take all the food material.
This is true.
Huh?
I have a few other things.
Yeah, I'm going to keep it minimum because I'll leave everything for her. I knew he was the CSI leader in the 80s, that I knew. I also knew that he was the department chair because I was a junior faculty member and he shepherded my tenure case and many others in the department at that time. I also knew that in the middle of being a department chair, he created this national program and created Ultra Lab, which I think is probably, in my child's eyes, the most cool-looking lab.
Recording has started.
This is the voice of God. Created, I think, one of the most cool-looking spaces on lab in my eyes. So, Bob has many prestigious awards, and I'm sure we're going to get into some of those in a little bit. And so, without taking any more of the time, I invite Bob to tell us about synchronization dreams.
The schedule also. So after Bob's presentation, there's a break with the lunch, and then after that, there's going to be training.
So after Bob's presentation, we'll have a break with lunch, and then there would be a sit-down conversation, which would be more interesting than what I just said.
Yes, so we're going to take. Yes.
Well, I want to thank, I wish they'd raise this podium up about a foot.
I was thinking the other way.
We could lower. I often wish we could lower you about it, but.
I want to thank MHI for inviting me to give this talk, especially God, wherever he is. Are you there, Sri?
I'm here.
Okay. And when I was asked to do this, they said I could talk about anything that I wanted to talk about. And I thought, well, all my ultra-wideband work is so recent that some people still remember it. So I'm going to talk about stuff that happened all the way back in the 60s and 70s, maybe the 80s. If I'm lucky, I'll get to 1990 before we run out of time. And the thread of this, most of my work has involved various problems in synchronization. And so that's what I want to talk about today. As you know, maybe you don't know, Professor Ghulam was hired as a regular faculty member about 4 or 5 months before he came up to Stanford and recruited me to come down. And it was quite different in those days. We started working on various topics, and one thing that he wanted me to do was participate in writing a book with him. And so I wanted to show you a book review. So this was a curious kind of a book review. That was the start of the review. And indeed, we did write about Secret Agent 00111, for those of you who think in binary, I guess. There's,
But it's a variable length code, otherwise it would be
whatever. Okay. So I want to tell you about one of the adventures in this book. And it has to do with a problem that the War Department was having with spies. And of course, when you're writing an information theory book, when you talk, who knows better about the price of information than a spy, you know? So it lends itself very nicely to little introductions. So here's a couple of spies in the War Department. These are actual spies that were in the British, had infiltrated the British Department. But we'll forget about them, they're just spies now. And so our fictitious War Department sent an agent to try to get rid of these guys. And so here's the agent. And he was a very good-looking guy. He knew all the tricks in the secret agent handbook, that sort of thing, you know. So they sent him to try to intercept these moles that were in the War Department before they could get out the information about whether plan number 1 or plan number 2 was going to be used by the War Department in their next escapade. And so there was only one problem with the secret agent. He was so easily distracted, he didn't get the job done. Anyway, the word got out, and here's the radio operator listening to the transmission. Is it going to be 1111, or is it going to be 2222, and so on. So the problem was this code was not very well put together. So there's the transmission, and if you see the whole thing, you see it's obviously 2222. You can't miss it. Well, the radio operator went to sleep, and he missed the beginning of this transmission. And he didn't listen all the way till the end either. And so, you see, if you look at it slightly differently, it's 1111. There's this problem of not being synchronized to the words. So, the cause of ambiguity is the fact that an overlap of 2 words is another code word, and so you can't figure out where synchronization is. Well, this was an introduction to the chapter on synchronization, and in fact, Saul introduced me to the synchronization problem when I came down here. And how do you avoid overlaps of code words being another code word? So you can, whenever you see a code word, you know that's it. It's not some overlap too. And the first thing that Saul discovered, maybe even before him, certainly was that you have these cyclic equivalence classes, and I'm demonstrating this for a code where all the words are 6 binary symbols. And you can only pick 1 word out of each class. If you pick 2, you're going to have a problem. And so we can demonstrate that pretty easily. I picked the word number 5 up there. You can see it's the binary expansion for 5 with the least significant digit on the right. There's 5 followed by 5. Well, we see 10s in overlap, 20s in overlap, 40s in overlap. They're all in that same cyclic equivalence class. That's the CE and NPCE. The NP means non-periodic. They don't have any internal periodic structure within the word, and I'll show you what the problem is later. Let's get the last 2. Okay. So let's say we pick the word 5 to be in our code. Can we pick the word 1 to be in our code now? Well, let's see. I'll take 5 and I'll attach 1 to it. It's in a different cyclic equivalence class. I'll look at all the overlaps. They will be different elements of those 2 cyclic equivalence classes. That's sort of a special result. Don't worry about that. But you don't see 1 or 5 in that collection anymore. So those 2 words could be in the code. Actually, I've got to look at the reverse 1 followed by 5 and check all the overlaps there as well. There's 3 more classes that I didn't show on the first slide because there wasn't enough space. These are also non-periodic cyclic equivalence classes. The numbers here are not relatively prime to 63, 2 to the 6 minus 1. And we take advantage of that numerical structure later here's the classes that have sort of periodic structures in the words. It's a three-tuple followed by the same three-tuple again, or a two-tuple followed by the same two-tuple over and over. You can't use any of these as code words. Say take the word nine. If nine's in the code, then nine's an overlap, so it can't be in the code. So just throw all these words out. So there were 9 non-periodic cyclic equivalence classes where we might be able to choose words to be in this code word. No overlap is a code word. How do we ensure that we can do that? Is that always possible? I only picked 2 to begin with to give you the idea of what's going on. So this is the definition of a comma-free code of length n with an alphabet x. No overlap of 2 words is a code word. That's the constraint for comma-free code. And the number of code words has to be less than the number of these cyclic equivalence classes, less than or equal to that. Somebody counted this using Möbius inversion and a little bit of mathematics. That was Guam and Welch and Basil Gordon from UCLA, published this in a paper in the Canadian Journal of Mathematics, if I remember right. And so the challenge is, can you get the largest possible comma-free code where the number of words is exactly equal to this number of non-periodic equivalence classes? I went a totally different direction when Saul told me about this, and I was just playing around with codes where you can eventually synchronize them. So this code's easy to synchronize. I see a string of zeros and ones. Those are code words. I just put commas in between them. It's done. Now I can construct another code by taking one of the words from the previous code, namely the 1, and attach it as many times as I want to any other code word in the previous code. And since it was only a 0, that's the set of words I get. It looks very much like what people used to call comma codes way back then. Well, I'll repeat this construction. This time I'm going to take 0, 1, 1 out, tack it onto all these words, and I get still more words, and they look more complicated in some sense. And all of these codes, except for the 0 one, have possibly an infinite number of code words in them. You want to truncate it at some length, of course, to be practical. Okay, so by the time I've removed the 0 as well, you begin to see structures of words. Okay. Now it turns out, well, let's see, what I need now. Does anyone know what zeros and ones are? Who knows what zeros and ones are? A student, a faculty member, anybody? Can you write a string of zeros and ones on the board for me? Anyone want to volunteer?
Volunteer, Mark.
Are there any students from my class in here?
For that, you go ahead.
If you want to pass.
Where do you want to?
I got a. How's that? Not much light up here. Oh, about 20 zeros and ones with a little space between. We got
Like
20. We gotta get 20 of them in there. So. Yeah, some on the front if you want. Well, that's a good start. It doesn't have to be 20. That's a good number. I ought to do it. Thank you. Now, what you have to realize is that I can take this string and I can uniquely break it down in words of this code. It's always possible. And it's because you can do things serially. The first thing I do is synchronize for code 0 up there. There's all the commas. I've broken it down. Then what do I have to do to synchronize in terms of code 1? I have to erase the comma before every comma, little comma. So, do I have to use my fingers for this? Is there a...
This is so new.
Okay. I'll do it down below. So this comma will remain, that one will be erased, that one will be erased, that one will be erased, that'll be erased, that'll be erased, that'll be erased, this one will stay, that'll be erased, that'll be erased, this one will stay, that will be erased, that one will stay, and these will stay. And I don't know what happened over here. So I've done code 1. Now I can do code 2. Is there a 0 on 1? Well, let's see. I don't see it.
You see the 3 ones? It's in that.
But I'm looking for the word that's precisely 0 on 1 with commas at each end of it.
So,
Oh, right here.
Yeah.
There's 0 on 1. So that comma gets erased. Thank you for the erasure. Now I have interpreted this in terms of words in code 2. You can iterate this whole process and break this down into string of words from this code. So I thought that was a pretty cool construction, and I published it in the Information Theory Transactions, and no one objected to it. There's lots of things you can prove about codes constructed in this fashion, like, and I won't go into all the details. Maybe Ubla can ask questions if she wants to about that. Anyway, I found out that there was a way to construct comma-free codes using this kind of periodic, not periodic, recursive construct. And so, specify an alphabet, specify a word length that you're interested in, and there's your first code. Take the smallest odd length word out of whatever code you were presented with and use it as a suffix on everything else. And you just repeat this until there's no odd words of length less than n in the code. And so that gives you the repetition part, and when you find there's no more, the words of length n are a maximal comma-free code. And that was quite a thing to prove, but it solves this conjecture that Galam had made about the fact that you can pick one from every equivalence class. Well, just to finish up this topic and get on to some more interesting stuff, I want to say that there's one problem. We did an example of length, we're like 23 binary codes, maximal. There's under 1 million words. Back then, when we did this in the 70s, that would have been a pain to try to store the code and map data into code words. That was a problem. Now we probably just say, what the heck, we'll put it in memory and let it go, you know? If you went up to length 60, 65, you need 38 petawords or something like that in order to be able to construct the code and store it. And there's an easier way to map data into code words, and that was the last thing that we did. I had been working on this problem and done some examples of mappings for small lengths. Showed it to Lloyd, and I said, Lloyd Welch, and I said, Lloyd, is there some systematic way of constructing these mappings so they're one-to-one from a string of data into an equivalence class? And once I get to the equivalence class, I can figure out what the right code word is to use from that class. And so Lloyd went home after he saw that. The next day he comes back with this construction involving various kinds of group theory and subgroups. And so here's the example for length 23. And there's a one-to-one mapping. If you put an appropriate data bit in for D and a string of bits in for X, plug it into that equation, the number B, binary expansion, is in a particular equivalence class. I'm going to cycle that and find out what code word to use that will be in my maximal comma-free code. No other data bits plugged into that equation will give me another word in that same equivalence class. So this is a one-to-one. So then, when we get that word B, we expand it in binary, and we put it into this shift register, cyclic. Time goes in a particular direction here, and we start erasing the commas in front of the shortest odd word lengths beginning with, well, I have 0 or 1. I'll always take the binary least expression. So let's remove the commas before the, I must have already bumped this once. Let's see. There we go. Original commas. Erase the commas before comma 0, comma. Erase the commas before comma 1, comma. And I've got to look for a word of length 3. And there's a 1, 0, 1. 2 of them. Get rid of those commas. There they go. Now there's some words of length 5 in here, I thought. 1, 0, 1, 0, 1. I missed one. It was 1, 0, 0, 0, 1, probably. Let's see. When I'm all done with this process, there's a 12 and a 13 length string in here. Get rid of the comma before the 13 length. And if I read this cyclically out of the shift register, that's the code word. This is easy to implement for words of length 100. It's a very simple algorithm. So we took care of the data mapping, and then I got out of the field. I didn't do any more work on this particular subject. So actually I did a little bit, because I started thinking about this. The capacity of a noiseless channel with that many symbols is just the log to whatever base you're working in of the number of symbols. That's the noise-free channel capacity. The number of words in this maximal comma-free code, if I don't push the button in time, say something, because I got 2 displays up here. I'm bound to look at the wrong one at some point. So there's the capacity calculation. Pretty simple. There's the number of words in the maximal comma-free code. And now if I want to figure out how many information bits words of length n of that number can carry, it's 1 over n log base 2 of bn. It turns out as the word length gets longer, you get more and more efficient. You have to devote fractionally less of your design to carrying synchronization information. So there's this there's trade-off. As the words get longer, you're more efficient, but you have to wait longer to get the first comma into the data stream you're observing. Assuming you don't start at the beginning of the word, this is that kind of a problem. Well, let's continue. Well, 15 years later, a student and I were talking about how we came back to this picture. And these numbers, like the 1, 2, 4, 8, 16, 32, and so that's the cyclotomic coset. This has to do with roots of minimum polynomials over G of 2, all that coding noise that the people that don't do coding, just it goes in and out pretty easily. But we knew how to map data sequence into one of these non-periodic cyclic equivalence classes, which can also be thought of as cyclotomic cosets. And these primitive ones allow you to produce minimum polynomials for a prescribed primitive elements in GF 60, well, whatever, to the n. These polynomials are over GF2. Now, what you can do with those is generate what are called linear feedback shift register sequences. If you know how to build the shift register, that's really cool because there are so many of these minimum polynomials. This is a very nice construct for someone who wants to do security work. They want to be able to change the code they're using. It's linear, that's not so hard. But outside of that, you have access to large numbers of linear feedback shift register sequences. So or M sequences, maximal sequences as they call them. So, I had a student, Joe, and this was 1989-ish, as I recall. I gotta push another button. There we go. And his thesis is on the design of a switchable pseudo-noise generator and how to build it in VLSI. He did that, and he was immediately gobbled up by Qualcomm. They said they needed someone with that kind of expertise. And he went on to be, vice president of Qualcomm, head of their Asian operations, all that sort of stuff. But what happened then, after we were doing this, by that time, the National Security Agency was watching our work. And that they, in fact, said, well, we'll fund you. This is about 1983 or 4. And so that they could look at everything we produced before it went out. And so we did some more work, and all I can tell you is they liked it so much that they put it in their own journal and wouldn't let us publish it anywhere else. So yeah, that was one of the interesting events. So there are open problems in this area. Anyone who can do this kind of work, synchronization work in channels which have insertion and deletion errors, if you can do something good there, either in coding or in information theory, those are all open questions. Whether anyone's really interested in the result, I don't know, but they're interesting mathematical questions. How are we doing? Not too bad. So there are several modes of synchronization, and what we're going to do later on will refer to the search mode, the acquisition mode, or the tracking mode for different pieces of research. What I want to do now is talk about some things that I found out when I was researching spread spectrum systems. And I'm going to start with sort of a preview of what it was like in World War II. And I know I could push this, it's probably cool enough now. Let's get this down. It may take a few minutes for the projector to warm up, but we'll all be able to see better then. So what this is a picture of a communication system, one end of it, that was supposed to allow President Roosevelt to talk to Churchill, that sort of thing, a super secret system. And you might think of it as wireless cryptography. The voice was sampled, and it was added modulo 6 to the key, and then that result was transmitted over the link. Now the key was a one-time pad, and as you all know, those are cryptographically perfectly secure, providing no one else has the pad. Okay, the keys were recorded on, believe it or not, phonograph records back at that time. They didn't know how to store lots of this sort of stuff easily. The records were made by Decca, and one was sent to the other end of the link across the ocean, and then they had two operators that would start them, get on the phone, let's start them now, and then they have to adjust the speed of the record players until they synchronized, and then they tried to keep them in sync manually while the conversation was going. So you can see the important words in this. Manually synchronized. The non-coherent reception is just referring to the fact that the carrier frequency was known, but the characteristic phase was not, and you're going to take up some of my time.
Sorry, I was going to say, this is like people being a delay lock loop.
Yeah, it's like people being in it, yes. So, that was the technology of the time. Now I want to point out a little bit about spread spectrum systems, which do have data modulation performed or controlled by a time-varying random or pseudo-random signal of some sort. That's what that key is that was in the previous system I talked about. But that system did not expand the bandwidth. The bandwidth of the data signal that was being transmitted was basically the bandwidth of the RF signal. So it was a secrecy system, but not a spread spectrum system. So when I started into history work, I looked for all three of these characteristics, and if I got that, I said, well, this is a spread spectrum system. Expansion of RF bandwidth as well, and a receiver processing that basically reduces the interference ratio by this ratio of bandwidths. So let me show you a sort of, this is out of my notes from way back when. Here's a transmitted reference signal. Here's the noise source. It's combined with the data signal and transmitted, and so the receiver knows what the noise source is. We send it separately over another link. And then, well, that seems kind of dumb. Just about anybody can figure out what's going over the link if you do this, because they both have access to these signals. The next step was to break that transmitted reference link, have a pseudo-noise generator here, another one in the receiver, and try to synchronize them so that what's playing into this modulator now is exactly what's playing into this modulator now. And that was a problem that stymied people for quite a while. Eventually, we have some examples of those systems, but these are all mid-1950s or later. There was another kind of system, rather curious. A delay line was built out of lump circuit devices that were switchable. Some of them were put in the transmitter. The rest of the delay line was put in the receiver. So when you transmit a signal down through this, by the time it gets over here, it's just delayed. But in between, when you look what's being radiated, it's moving around in a strange shapes because you don't have a complete delay line. This was, I'll show you just briefly one of those in about, that'll only take a few seconds when we get there. So, here's another World War patent, okay? The technology wasn't sophisticated, and neither were records played by Decca. So what I would like you to do now is close your eyes, keep them closed for, I'm serious, Jerry. Close your eyes and listen to the words of the inventors of this patent.
Briefly, our system as adapted for radio control of a remote craft employs a pair of synchronous records, one at the transmitting station and one at the receiving station, which change the tuning of the transmitting and receiving apparatus from time to time, so that without knowledge of the records, an enemy would be unable to determine at what frequency a controlling impulse would be sent. The two records may be synchronized by driving them with accurately calibrated constant speed spring motors, such as are employed for driving clocks or chronometers. It is of course necessary that the record strips at the transmitting and receiving stations, respectively, to be started at the same time and in proper phase relation with each other, so that the corresponding perforations in the two record strips will move over their associated control heads at the same time.
Okay, you can wake up now. Did everyone picture what was going on there? What were the important words that you heard in the description? Synchronous. Okay. Synchronized. Constant speed clocks. Started at the same time in proper phase. They're talking about it. She's talking about a spread spectrum system, and when I say she, who is of course Hedy Lamarr, thanks to Oogly Lamarr, inventor for reading that. Okay, so let's get off at Hedy Lamarr. I said I'd show you a transmitted reference system. This is one that I really like. You may not be able to see all the details. So here there's a noise source, and it's transmitted from transmitter to receiver. So that's the transmitted reference. But before you modulate it, they tap it off and they do some filtering of the noise source. Then they modulate information on it. Gee, a genuine voice signal, okay? And send it over another link. And if you don't know what filtering's been done, and you're listening to this, you can't spoof or jam this system without reconstituting this filter in some way that you can't see. That was a very interesting version, and that was, that was patented back in, filed 1943, patented 1947. There must have been some problems with it, and indeed there probably were. There is no sort of random control of these filters. It's been driven by a chronometer, and that's all. Then there was another system that was built around 1950 that stored pseudo-random noise or pseudo-random numbers as the lengths of the white area that you see. And as you travel around, you read different pseudo-random levels. And these were spun, and information was modulated on this by, turns out, time shift modulation of data. And that's a test bench over there on the right side. I'm not going to go into the details of this patent. That's a picture from the patent. The wheels are there, different. These are the wheels and on. These are different places tapping off the pseudo-random noise, depending on whether you want to send a 0 or 1 or some other quantized level. There were some interesting optical things that were done in this, including an optical multiplier. But I think the real contribution here was this was the first patent where I saw there is such a thing as processing gain that's related to bandwidth expansion. And if we build the receiver right, we can knock down external interference by that processing gain, or we can raise our signal, let's say, by that processing gain level. And they demonstrated a 40 dB processing gain, which is pretty healthy when you stop to think about it. I could say a few more words about that if my mind doesn't go off track later on. So, you hear about spreading and despreading when you talk about spread spectrum systems. And the objective of spreading is to take a narrowband signal, transform it in some way so the bandwidth gets a lot wider, okay? And then at the receiver, you undo that process. That's despreading. So let's imagine that there's information modulated on here. It's either +1 or -1. I'm either collecting this waveform or this waveform. This is coming into the radio, and inside the radio I have a record of the modulation down here. Now they're not quite in time alignment. These are the same times, and obviously they don't line up. When you multiply them, you get this funny picture. This is the bandwidth of either of these input, the power spectrum of either one of these, or energy spectrum. This is the energy spectrum of the output. And now let's slowly synchronize these. You'll see the top wave move a little bit, moved over. All of a sudden it's in a position where the switches here line up with the switches here. You start seeing some shaking of the band. It will disappear unless something nice happens. We'll go a little bit further. Now we see most of the time the product is 1. We're sort of partially lined these up. We're now in the acquisition phase, let's say, of this process of trying to synchronize. And what happens is you start seeing lines appearing in the spectrum down here. As you approach perfect synchronization, all of a sudden the output is the data bit that was modulated, and the bandwidth has gone way down to 0. If you had put an interfering signal along with this in, the interfering signal would have gone through this whole process, and it would have energy spread all over the spectrum down here. And you can filter out the parts you're interested in, get rid of all that excess jamming energy. So that's the concept of spread spectrum. And this is actually, I just went on and, Mathematica pulled out a random sequence and drew the pictures. There's nothing special about the particular code I'm using Well, this kind of modulation, plus or minus one pseudo noise and probably binary data, was used in this 1952 JPL system. There's the generator that generates plus or minus random signals at a very high rate. It multiplies the slowly varying signal here. And it's recovered here by multiplying by that signal again. And low pass filtering to get rid of any noise that might have, or any interference that might have been in the system. What they didn't know at the time was how to cleanly synchronize this pseudo-noise generator to this pseudo-noise generator. So they did something different. They sent another pseudo-noise signal, whose relationship to and one signal they knew, and they just added it in. At the receiver, they tracked the N2 signal and adjusted synchronization, and the N1 signal was in proper sync. And so they used what's referred to as separate channel synchronization here to accomplish that. They did it with an unmodulated signal, just a pseudo-noise signal, no data. You'll notice one of the inventors is Ed Recton. He was on our faculty for quite some time, passed away a couple of years ago. Very interesting person. He was at one point an undersecretary in the Department of Defense for Telecommunications. He was the chief executive officer, I think, for the Aerospace Corporation for a while. Anyway, for what it's worth, when I was doing this work, and this was history work I was doing around 1980 or so, this information about this was still classified. I had to call up Eb. He said, contact Walt Victor, I'll talk to him and tell him you're okay. And Walt Victor was at JPL, and he got this report declassified so I could read it and pull out a few nuggets for the spread spectrum history. Well, MIT was doing this too. They called this noise modulation and correlation. They were doing teletypes, workspace transmission. They are the first people I saw that actually indicated that they could synchronize without separate channel information or transmitted reference stuff. I don't know whether they were the first. It's the first place I've seen someone claiming synchronization without going over a separate channel for sync information. The cool thing was that when I was doing this work, Paul Green got me started. He's the fellow on the right. And he gave me all his documents from Lincoln Labs when he was working on Nomax systems. And they were all, synchronous, scratched out, all that sort of stuff. And they were cleared, so he could give them to me. It was a nice, as I say, nice features. What was interesting in this was when they tested it on an HF cross-country link, they had problems with multipath interference. And so Paul went to Bob Price, who had been working on how to deal with multipath, and he had designed a multipath combiner, which they call now a rake combiner, a particular filter that listens to all these different signals and somehow gets them lined up so they behave in some sort of nice fashion for detection. This was Bob Price's rake combiner. That's not the whole thing. It's just that little filter that does the combining process. Magnetostrictive delay lines at the bottom are part of it. The rest of these are just sections which do multiplication and averaging kinds of things. Well, as I said, all these guys' theses actually were written at Lincoln Labs, and they were all classified, so they couldn't really publish them. And shortly after they graduated, some nice, interesting things happened. So I have a little introduction to this. Imagine how you'd feel if you were one of those PhD students who just done this great piece of work. and your thesis had been classified secret or top secret or whatever it was, and then you pick up this science fiction book by Theodore Sturgeon and you start reading. And the setting in this story, it's a spaceship which is sent out to go to this distant galaxy and learn about their technology. And this galaxy is surrounded by some sort of barrier. And this barrier was controlled by a little planet called a planetoid inside the galaxy. And it checked to see whether anyone was coming in. And if you managed to get through the barrier, you were immediately shot down by a missile with magic powers. Okay? So as we start in on this, the captain of the spaceship is interrogating the missile expert.
Got it yet, Mr. England? What? Oh, I guess I was off base about the jamming. Suddenly it seems to me that's so obvious it must have been tried and it doesn't work. Right, it doesn't. That's because the frequency and amplitude of the control pulses make like the purest noise. They're genuinely random. So trying to jam them is like trying to jam FM with an AM signal. You hit it so seldom, you might as well not try. What do you mean random? You can't control anything with random noise. They can. There's a synchronous generator in the missiles that reproduces the same random noise peak by pulse. Once you do that, modulation's no problem. I don't know how they do it. They just do. The Luani can't explain it. The planetoid developed it. The same random?
Thank you very much, Todd. If I give this talk again, I'll give you a free trip to wherever I go. But again, if you read the words here, of course, there's that synchronous generator reproducing that same random noise. Great story by Theodore Sturgeon. If you try looking it up, you have to find the anthology that the story is printed in. I just managed to get one on Amazon for about $5 plus postage, so it's an ancient book. Well, enough. I'll forget about this. This is simply the work of Ernst Gilliman at MIT, and he's the guy who designed the broken delay line split into two parts to do basically not really spreading the spectrum. He was spreading time in that particular case, but I classify it as with the same principles. So when you think about synchronization, there's lots of things that have to be synchronized in a receiver. And sometimes you're in a class and you learn how to build a phase lock loop. That works fine on cosines, but how do you deal with it when it's modulated? How do you synchronize the spreading code? There's carrier sync for just the main oscillation that gets this propagated. And then there's code word sync, bit sync, all these sorts of things have to happen. Some of the clocks that you can use are geared together in some way. And that's nice. The carrier and the spreading code are totally different clocks typically. So I certainly didn't work in all these areas, but I did work on the comma-free stuff and on the spread spectrum things for quite a few years. And I wanted to show you my favorite books, so I took a picture of them. And I'm going to get this started. You probably can't read that very well. The first three here are actually papers. Those papers always come before books, typically. So the first three were what I thought were the landmark papers. And one was, again, Ed Ruckman's work at JPL in a paper by Jaffe and Ruckman on phase lock loops and building them so they could track vast accelerations. They were using these in a test range where they're firing missiles and trying to get telemetry back to the ground station. So that was work. And by the way, he told me once that he tried to patent the phase lock loop. Perfectly logical thing to do. He sent the patent description into the patent office, and the examiner came back and said, that's just an application of automatic control, feedback control. So they didn't pursue it, they didn't argue, but that died. John Costas here, very well known for building tracking loops when signals are modulated. The Costas loop's one of those famous things. John also built spread spectrum systems back at GE during the late 50s, early 60s. I think one of his was the Phantom system. And Andy, of course, did a lot of nice work on analyzing phase lock loops and loss of lock problems, things like that. So let me continue this. Go get the right one. That'll do it. Oh, there's Gulam again. His book on digital communications. Jack Stifler, the next picture, actually wrote the synchronization chapter. Bill Lindsay's there. And some other people you might know, Marv Simon, Jim Stoker, Heine Meyer. They were all familiar faces. The group of people that worked on this set of problems that were communication theorists was a fairly small group. We all knew each other and shared papers and that sort of thing. Well, who do you think said this? Doesn't that sound like one of our problems? Okay. Who said that? This goes way, way back. This is like 15th century, 1500s. Charles V, the Holy Roman Emperor, eventually became Charles I of Spain. All sorts of things were happening in Spain. How are we doing? How much time can I do one more segment of all this stuff I have planned? Is that okay with everybody? Okay. This is sort of far out stuff too. Stuff that was introduced to me by Bill Lindsay back in the, I think around 1979, 80, somewhere around there. And it's a study that was being done by NASA to put a large solar array in orbit, a geosynchronous orbit, and radiate the received power down at microwave frequencies to a gigantic antenna on the Earth. And they wanted to know what were the major issues in doing that. And again, it turns out, this one could have been motivated by an Isaac Asimov story. So maybe all of you engineers who want to be dreamers have to read more science fiction. You get some ideas out of it. You can see all sorts of negatives trying to get this array, and the antenna that you have to build up here to send a narrow beam down to even an array that's 5 or 6 square miles or something like that on Earth. That beam has to be very narrow to be efficient. So you need a good sized antenna in orbit. Then when the antenna's in orbit, when it heats up, it bends, it flexes, all those sorts of things with problems in pointing. 36,000 kilometers above the equator, so it's pretty far away. So the question is, how do you do that? And the concept that was put forth was that on the back of this large solar array, every so often they would have a transmitter that would be powered by that section of the array, and it would create a microwave frequency and it would go down. Then the problem was you probably had 1,000 of these transmitters on this bending array. How do you get them to cooperate so that they do really form a beam that lands on this target on the Earth? Well, that was the problem, and it was proposed that you use what's called a retro-directive array to do that. You send a signal from Earth up here that says, here's where I am, and that array has to send the signal back in that direction. And how do you accomplish that? Well, As you can see, the whole idea was patented back in 1973, taken up 1978 to 81 by NASA. As soon as Ronald Reagan came into power, he axed that program, so it died in 1981. Came back, resurrected in 1999 for a while, and now if you look up solar power satellites and Wikipedia, you'll find out that Japan's thinking about putting one up in 2040, and I don't know if we're doing it anymore or not, but some interesting things came out of this. So there's the problem that I focused 3 of my students on working on this pointing problem. I want to show you the first retro-directed array, which was passive, not active. It was used on test range. It's called a Van Atta array. And what happens is that a wavefront is propagating towards the array, and they try to turn pieces of the wavefront around and send them back out. If the total time of propagation in, over, and back out to this line, this wavefront, is the same for each of these different paths, that wavefront will go back out the way. So we can, it doesn't make sense to use this in that retro-directed case. Can you add power to it? What can you do? Well, there's something called an active retro-directed array. Let me show you one of those. So here's the antenna on the ground that they used to call the direct antennas back in those days. It's the array to which you have to beam the power. And there's an antenna down there sending out the pilot signal. Now here's the array up in space. Here's the antenna. This turns it around, adds power, and sends it back. Somehow you have to measure the time of arrival differences of signals at these different points so that you can compensate to get them to come back and be perfectly in phase and add up down here. The problem in doing that is that you have to transfer time or phase information to all these different transmitters on this big array, and they have to be exactly in sync when they get to those transmitters. Then you can do the time measurements or the phase measurements and send the signal back. Here I'll show you one way that's done. So I mentioned that this was the problem. And here's one of these modules. The signal comes in. It gets mixed with the reference signal that's coming from the timing network. And when you down mix, what do you get? The same sign you saw, but with a plus D instead of a minus D. That's enough to compensate the signal so that when all these go back to the ground, they're in perfect synchronism. Well, I had one student, Kang, who worked on, gee, can we use a frequency offset? Because, well, actually, let me back up a second. There's some problems that I needed to mention. How do you hear this distance pilot signal when all these antennas around you are shouting at the same frequency going back down? That's one issue. How do you distribute the time and phase information over the array? How do you prevent a false pilot signal? Suppose I'm ranch in Arizona and I need some power. Let me just send up one of these signals and build a little array and steal some power. Just move the beam. Okay, how do you do that? And how do you deal with all the array distortions? Well, that's what the retro-directed antenna, active antenna design is supposed to do. So I said, well, let's solve this by sending up a frequency offset signal. Then you have to figure out how to measure time and compensate for all the issues and changes in frequency. That was one thesis. I put this one in for my 562A students. The second piece of work was by Raimundo Sampaio. He was a student of Roberto Tamarcas down in Rio, and Roberto sent him up to work with me. And his idea was, well, let's make that upgoing signal a suppressed carrier, so there's no information at exactly the frequency we're interested in, or very little. And let's make it spread spectrum so it's not easy to steal or jam or whatever someone might want to do. So the question that he went to work on is, how do we protect the code tracking loops in the antennas up in the sky from this high power signal? And his thought was, well, let's put in some filters before all the correlators in these tracking loops. So we'll put a filter there. And here's the incoming signal with lots of interference on it. So it didn't take us long to really get the carriers out of this and just deal with the modulation that's on the carriers in this model. And we did that. Students have just seen this, I hope, by now. And then we went around and we said, well, if we do a little more work, make a couple more assumptions, we can sort of embody this in something that looks almost like a phase lock loop model. Now, mind you, here are the filters that we haven't figured out yet. Whoops. I think I haven't messed up all of you. Okay. So there's a typical phase lock loop kind of a thing. Where are those filters? They're buried in this nonlinear curve here. They're buried in the noise, effective noise pile up there, and probably in this gain down here. And these are messy calculations to try to figure out how can I maximize the slope of this curve so I get good tracking relative to the noise level that's being added in there. So we got this very messy expression. Integrals all over the place, integrals of this times that, and all this sort of stuff. And we couldn't see how to do the optimization until, and this was very interesting, until we transformed all those integrals into inner products and started thinking geometrically in a Hilbert space. And believe it or not, at that point we could do the optimization. We found out the best filters. And of course, he graduated. The most important part of all, I guess. And the last thing I'm going to talk about, which is kind of interesting also, that came out of this record-directed study, was Alex Netch's work. And it wasn't so much the work, so I'm not going to dwell on it too much. He figured out how to sort of combine signals pairwise at a time to get a tree and reduce the amount of wiring that you needed, the tons of wiring that you'd have to haul up into orbit to organize all these antennas. And he built those little things that did the combining. Well, that was his first introduction to electronically stabilized arrays. And it turns out people are still interested in that sort of thing, very much so. And so it turns out when these problems came along, Alex, who ended up being sort of a troubleshooter at General Dynamics and then at Hughes and then at Raytheon, they filtered down to him because no one had a great deal of experience with all of this. And so the people who were funding him, I think they were from NASA, they said, Alex, why are you wasting your time at this company? We're going to set you up with a little company and you'll be sole source as a consultant to whoever gets these big contracts to deal with electronically stabilized arrays. So these are two programs that I think are partly on Raytheon now. I don't know who the prime is. But this idea was, again, to measure time differences of arrival coming up to these array elements, but this isn't for record directivity. This is to get a sense of where those elements are relative to one another. And if you send signals from different places up, you can get sort of a 3D image of where the antennas are and steer beams from there on using that information. This was supposed to be 300 meters or so in length, It's an antenna that was supposed to fold up into the nose cone of a big missile. When it gets up in orbit, the antenna would spread out. What I haven't figured out completely is, well, it looks like there's maybe two of them. So this will have a narrow beam in one direction on the Earth and a wide beam in another. And if this one's oriented at some different angle, you can probably pinpoint where signals are coming from. And so it's sort of a spy satellite kind of thing. ISIS is another program. This is a flexible balloon. There's an array of solar cells on top that provide energy. There's an array of antennas on the bottom. Now, this balloon is flexible, so this antenna keeps changing, and they want to know where each of the antenna elements are. So what do they do? Instead of tuning from Earth like we do here, they have separate sources inside the balloon that broadcast out to the antennas, and they can locate them precisely and then figure out how to build beams in different directions. I have a few more slides, but I think this is a good place to stop because my voice is going. And do we have something to drink or eat here somewhere? Where do we go?
When you're done, then I'll tell you what happens.
I'm just going to keep going.
No, the food is ready.
What did he say? Anyone know this quote?
Oh, there's so many. To be or not to be, that one?
Act 1, Scene 5. The time is out of joint. Okay, so that's been the history of my life. Anyway, thank you very much. I guess there's going to be a sort of an informal discussion after you get something to eat.
So let me make a few announcements. So what's going to happen right now is that we're going to have fantastic food and drink.